Hello everybody, and welcome to part 2 of our video series on dose ratios and monitor unit calculations in radiotherapy. Today we will be talking about two additional types of dose output ratios, namely the tissue air ratio and tissue maximum ratio. These are extensions of the types of ratios and concepts we talked about in part 1 of this series. So if you haven't seen part 1 yet, I would suggest you go back and watch it before you watch part 2 here. But if you have seen part 1, well, let's get started. Just a quick review about what we learned in part 1. So what do we know when we calibrate a treatment linear accelerator? When we calibrate our LINAC, we start with our calibration statement, which would read something like for a 6 MV beam, at 100 centimeters SAD, at a calibration depth of D max for a 10 by 10 cm field, we know that we have set the output of the machine such that one monitor unit recorded by the machine is equal to 1 centigrade of dose at our depth of calibration, D max in this case. So we know the dose for one field size at one depth for each beam energy of that treatment machine. And what we're discussing in this series of videos is how do we go from our calibration conditions, field size, depth, setup, to the conditions of the patient's treatment, where we will be at a different depth, using a different field size within the patient. So we're discussing the idea of the output factors or output ratios that we use to calculate the dose at the depth and for the field size we need for treatment. Things such as percentage depth dose, and what we'll talk about today, tissue air ratio, tissue maximum ratio, and any other factor that may affect the output of the beam during treatment. Let's start with the tissue air ratio, TAR. It's a bit outdated as it's probably not used in the clinic anymore, but the concept of what we're doing is very relevant to all the other dose output and dose ratios that we'll talk about in this lecture. So for the TAR, what we're doing is we set up and we make a measurement of dose in air at a given SAD or a given distance from the source. We then put the ion chamber, put our detector inside of a phantom, and we measure the dose delivered at a given depth in the phantom. But keep in mind, we're exactly the same distance from the source in both setups, in air or in the phantom. In this case, it's the same SAD for both treatments. We would also have the same field size at the point of measurement in both cases. And so in the end, basically what the TAR is a ratio of dose in air to a dose in tissue at a given depth in your phantom or patient. Our next dose ratio is the tissue to phantom ratio. Basically for this ratio, what we have is we've made measurement of the dose at some depth T0 in the phantom. But what we want is dose at a different depth D in the phantom. So what do? We move the phantom, and then we make a dose measurement at this new depth. So the TPR is just the dose at depth D to the dose at our original D T0 position. So what have we done for this? We've basically taken our phantom, made a dose measurement at one point, then we've moved the phantom up, and we've made a dose measurement at a different point. In both of these cases, we're still at the same SAD, and our measurement point is still the same distance from our source. So really, the TPR is just the ratio of dose at one point in the phantom to the dose at another point in the phantom. So our next dose ratio, the tissue maximum ratio, is really a special case of the tissue phantom ratio. So if your point DT0, where you made your original measurement, is at D max for your beam energy, then your ratio is called the tissue to maximum ratio because you're measuring the ratio of the dose at a given depth to the dose at D max within the phantom. So it's basically the ratio of dose at one point in the phantom to dose at the depth of D max in the phantom. So we've talked about several different types of dose ratios for calculating dose at different depths within a phantom or a patient. So let's briefly discuss when you might use one versus the other. So if you have an SAD isocentric setup, like we see on the left, you've made your dose calculation at your T naught depth, which is probably D max, and you want to know the dose at a different depth in your phantom. What is it that you do? Well, you move your phantom up so that your point is deeper in the phantom, and then you make your dose measurement at this new depth. In this case, you moved your phantom or your patient up, and the distance of your measurement point from the source is still the same. In this case, you would use TMR or TPR as your dose ratio factor to go from one depth to another depth. Now, if you have an SSD setup, what would you do? You make your dose at your DT naught depth, probably D max, and then you want to know dose at a different depth, you would move your chamber further away and deeper into your phantom, so your phantom stays in one spot. And you would make your measurement of dose at this new depth. If you want to know dose at a new depth where your patient or your phantom has stayed in one spot, but you've moved further away from the source, then you would use PDD for your dose output factor. So in this case, you've moved the point of measurement and kept the phantom at the same spot. Aha! Let's go back and talk about our inverse square factor again for a moment, because it could show up again in a different point if you have a treatment linac that was calibrated in an SSD setup, but then you want to do your treatment in an isocentric SAD setup. For instance, we have a linac that's calibrated at 100 centimeters SSD, and our patient is treated at 100 centimeters SAD isocentrically. So in this case, we would see that our source to calibration distance on the right there is actually 101.5 cm. So that's 100 centimeters for the SSD setup. And then we were at Dmax for, say, a 6 MV beam, we would be 1.5 cm deep in the phantom. So a total source to calibration distance of 101.5. However, when we treat the patient, we're at a total distance of 100 centimeters away because we've moved to an isocentric setup. So we have to calculate what's the inverse square factor for that difference in distances between our source to calibration distance and our source to phantom, our treatment distance here. So that's basically our source to calibration distance divided by our source to phantom distance squared. So in this case, 100 centimeters for SAD plus 1.5 cm for D max depth divided by 100 for our SAD setup. And that gives us the inverse square factor that we have to account for during our output calculation. Are there other output factors besides just the factor of going from one depth in our phantom or patient to another? Absolutely. So let's discuss some of those. For instance, what about our scatter factors? So these describe the dependence that the output has on the field size we use for treatment. And we talked about field size dependent a little bit back in part 1. So these are typically broken up into one or two different scatter factors. So one of them being how the scatter off of the collimator that's used to define the field size affects our dose at a given point. So if you change the field size, we've changed the amount of scatter off of the collimator that gets to the point where we're measuring dose. And so we calculate a ratio factor of the dose for the field size we're using for treatment divided by the dose recorded for the field size we use for calibration. Also, that change in scatter affects or a change in field size affects the scatter conditions inside of the patient or treatment during the dose measurement. So when you add a patient there, now we have this new collimator/phantom patient scatter factor. And so that's just the ratio of the dose for the field size delivered to your patient or phantom divided by the dose measured during calibration conditions. Also, there are transmission output factors. So the beam intensity is affected by any attenuator that modifies the beam's shape or intensity. So anything you physically attach to the machine that interacts with the beam and modifies its intensity should be accounted for in some form of a transmission factor. So plastic trays or anything that supports field shaping blocks, physical wedges, if those still exist anywhere, these modify the beam intensity, and so we need to know how it modifies the output and the dose delivered by the beam as a function of field size here. So we will make these measurements. These will be plotted like you see here, and they will be included in your output information books that are in dosimetry or the PDF files that are shared. Another output factor is the off-axis factor. So currently, everything we've talked about is measuring dose along the central axis of the beam. But what if we're interested in knowing the dose off the central beam axis a few centimeters, as indicated here by the red dots? So two equivalent quantities are used that you might see in the beam information that's used in your clinic for calculating dose output. The off-axis factor or off-center ratios, these are just two different names for really the same thing. And so what we see is this off-axis factor is a function of x, distance off-axis, and depth within your patient or phantom. So it's just the dose at a given depth at a certain distance off-axis ratio to the dose at that depth on-axis. These off-axis factors are tabulated as a function of both depth in the patient or phantom and distance off-axis. And again, these tables are included in the dose output information that's shared by your department. Either it's a printed out binder that's somewhere, or these are PDF files on a shared drive. And you would look up these factors and include them in your calculation of dose or monitor unit. A special type of off-axis factor is known as the wedge factor. So this is basically the factor of how much a given wedge used for treatment affects the beam at different positions off-axis. And so you would have tables tabulated as a function of wedge angle as well as distance off-axis, as you would see here. And these are typically tabulated so that in the center of the field, your dose is 1, and then you have a ratio to that central axis dose as you go off-axis for each wedge angle. As you can see here, some plotted profiles for some dynamic wedges for different treatment machines. And you can see as you go off-axis for an open field, you get these little horns on the edge where the dose actually goes up a bit. But then as you go deeper and deeper into the patient, this profile rounds off and becomes smoother and begins to round on the edges. And on the right, we see a dynamic wedge profile for several different wedge angles, and you can see how that changes from central axis off-axis. So we've been talking about these dose ratio factors forever. Let's finally talk about how you would actually use all this to calculate dose. So we have a general equation for what the dose would be at any point in our water phantom or patient, and it can be calculated using this simple formulism here. So our dose is equal to our monitor units delivered by the machine, our output, our inverse square factor, and our depth dose factors. So again, these are the monitor units that are delivered during the treatment. Our output that's calibrated under calibration conditions, 1 centigrade per monitor unit typically. Any inverse square correction that has to be made if we've moved from, say, SSD to SAD setups. And then our depth dose factors, our PDD and our TMR, etc. Then, if there's any other factors involved in the treatment, we would also include them in the equation here. These would be like scatter output factors, off-axis factors, wedge factors, tray transmission factors. Anything else that's going to affect the output of the beam is also included as a ratio factor here in this equation. Okay, that's it for part 2 of this series. Once again, if you have any questions at all about what we've covered, please leave me a comment down below. I'll do my best to answer it. If you want to see more videos, please leave a comment, suggest a topic. I'll do my best to get a video made for you. And again, since we're on YouTube, I'm morally obligated. Please like this video, subscribe to the channel. Let us know you support what we're doing so we can make more content for you.